Well, fiber technology is at the heart of optical communications. We all know that. Throughout these decades, this technology has been very successful in developing better and better solutions and overcoming the most difficult challenges as they have appeared. Today, probably one of the most demanding ones is the capacity crunch, okay? So at the organization, we thought that our community would be very interested in learning how this can be addressed from the perspective of the optical fiber technology. Right, our next speaker does not need any introduction or presentation. I think that I do not exaggerate if I say that Professor David Payne, the director of the Electronics Research Center at the University of Southampton, is a living legend of optical communications. He has played a leading role in many of the top breakthroughs in optical communications, including the discovery of the thorough dispersion point in optical fibers, the erbium doped fiber amplifiers, that, remember, powers our current internet, and most recently, in the field of high-power fiber lasers. Ladies and gentlemen, Professor David Payne.
Great. Thank you so much, Jose, my old friend Jose Capmany, who is to blame for inviting me to speak once again as a plenary speaker at this amazing conference. We've just heard that this is the 41st, and I have been to all 41. And I figured out I figured this cost me about 100,000 euros. So, but I would also like to point out that this is the International Year of Light. And of course, maybe many of you will know that Valencia is often referred to as a city of light. So this is very appropriate indeed. But I thought I should start by showing you what the British Post Office thinks of photonics in this Year of Light, because this is actually two stamps which have been put out in celebration of the Year of Light. This apparently is an optical fiber and a cat's eye. Now, why am I showing this? First of all, this is an artist representation of what an optical fiber looks like. What it actually is, I have no idea. But I'm trying to make a serious point here that, of course, Charles Coward, 1965, often thought of as the father of telecom fiber optics. And the cat's eye road markers, which you see on the center of pretty well every road, was also a British invention by Percy Shaw in 1933. Now, I have to tell you that the cat's eye this year has been superseded by photonics, a little device which no longer is just a retroreflector, but actually has a silicon photocell and an LED emitter in it. So time does move on. And that's part of the theme of my talk. So I thought you'd like to see my credentials for predictions, which is what you're supposed to do in plenary talks. So this is me in Ecoc 1975, when I was on the technical program committee. And I made this very famous statement in Ecoc 2002 plenary, which is, bandwidth is like healthcare, you can never have too much. Remember, 2002 was the great crash. And I then was extremely embarrassed by the fact that for the next 10 years or so, we had too much bandwidth. But that, fortunately, in the longer term, I was right. So part of my theme today is to talk about just exactly what can we do about the new technologies. But what I also want to do is deflect the blame a little bit by putting up a paper, invited paper from Emmanuel Dissevier, who will be talking shortly on Wednesday in the Year of Light celebration, in which he states, written in, as you will see, 2006, 10 to 20 years from now, optical networks will have to carry vastly increased amounts of internet traffic. Today's knowledge already points to ultimate technology limits in the physical layer, foretelling the end of the so-called optical Moore's law. And that was a very prescient statement, because that's pretty well where we are today. So then I thought, well, I'll go and have a look and see what the Internet Society thinks about all this. And I pulled this up directly from them. And these are the things which they are suggesting that we need to do to improve the capacity and provide what everybody wants, which is gigabit to the home through optical fibers, universal access, as we've just heard from the previous speaker, in wireless at very high bit rates, and so on. And so you can see some of these are obvious. Technology to improve capacity. Of course we want that. Innovation to reduce traffic. Bad news, guys. That's not going to work, right? Nobody wants to have grooming, limitations on your bandwidth and all that sort of stuff. Investment to add more capacity. Well, that's good for us, of course, because that increases the business opportunities. Extend the network, as we just heard in the previous speaker, and increase the speed of light in the fiber. Right. Okay, we'll see what we can do about that. So these are the things I want to talk to. Technology to improve capacity and increase the speed of light in the fiber. So here we go. So this is my slide from 2002 plenary. I was talking about optical spectral efficiency. I noted the fiber transmission window. We had about 90 terahertz available. Amplifiers are the limiting technology. That was painful to say. Whereas the EDFA is today the limitation actually on the bandwidth that you can get from a single fiber. And towards 3 bits per hertz requires better wavelength control. So what have we done since then? There's a lot of talk about possibly moving the bandwidth window out to 2 microns. I will be talking about that. That would bring us up to 130 terahertz available. We now have amplifiers, thulium, holmium, and others, and which are very, very good amplifiers. And 16 bits per hertz, perhaps, is what we're talking about in practical implementation, and there's been a huge number of excellent publications in that area, using sophisticated phase techniques. And of course we have multi-core, multi-mode fibers, which is kind of the last resort, if you like. And there's an interesting question about that, which is, optical fiber today costs about $8 a kilometer. Incredible, isn't it? And so do we really care if you have to just put a lot more fibers in? Do you really gain by putting in lots more cores? Interesting question, and it's one that's exercising fiber guys all over the world. And then if you have a multi-mode, then potentially only one fiber but lots of channels in it. So that's good news as well. But I want to start with a question. Can we make a lower loss fiber? Because if we could, that would mean that we would be able to put less power in and the limitations caused by nonlinearity would be reduced. So this is a slide, and it's so old that I can't even find out who to attribute it to. So if anybody knows, please let me know. And it's pointing out that we have the classic window here, right here. This is silica. And we see that we have it at 1.55 microns minimum loss, caused by a balance between the scattering loss and the infrared multiphonon vibrations. But look at these other ones. There are other materials out there. that are known. But of course, it's all very well, but nobody wants to work at 5 microns, right? Why? Because you don't have proper and decent, efficient emitters, and fundamentally you have noisy receivers. So let's add something else to this, which is a reasonable band that we might want. And what you see then is that we have silica, our favorite, but there are others. Beryllium, calcium, combinations, then of course the famous Z-blan. And that would give us potentially a very much 10 dB improvement in loss. Would be really interesting, wouldn't it? So theoretically 0.03 dBs per kilometer appears to be possible. And the reason that these things were abandoned was very simple. It was cost and simplicity of manufacture. Silica turned out to be such a wonderful material. It's mechanical, environmental, robust, which is very, very important. And a lot of these other glasses, such as zinc chloride here, actually dissolves in water, so not a great idea for undersea systems, right? So, but, I wanted to leave you with the question, which is, do we really, really want to be able to do, for example, transatlantic, transpacific, unrepeated systems? Because according to theory, you actually could do that. So you will notice also that all of those materials moved us to longer wavelengths. And so the question then arises is, do we have amplifiers at longer wavelengths? And I'm delighted to say that we have shown indeed that you can. And this is the thulium-doped fiber amplifier, the holmium-doped fiber amplifiers, both of which are excellent amplifiers. It pains me to say it, but probably better than the EDFA. Very broad band, giving us a combined amplification window from 1650 to 2150. So there's lots of space out there, guys. So let's ask the question then, can we beat silica? Well, of course, as you will know, we could use air or vacuum. And this is the hollow core microstructured fiber, which is well known. And for those of you that want to have much greater detail, I would recommend you go and listen to Philip Russell, who will be giving a tutorial on this topic exactly. But let's have a look at some of the high-level issues related to this kind of fiber. It works because of this clever band gap structure here in the cladding, and that means that most of the light, I say most, travels in the core here in the middle and doesn't penetrate into the glass. So typically the glass penetration is 0.05% or less, so we would expect ultra-low nonlinearity, lower loss, and indeed very high power transmission in my other area of interest, which is high power lasers. So here's some examples. You know well about these. So let's look at the state of the art. Is this technology really going to make it out there into the world? And there's been a lot of work, Bath, Corning, ourselves at the ORC, over the years, trying to get the loss down to match silica, 0.2 dBs per kilometer. Have we succeeded? No, not yet. But it's still looking good, actually. So the challenge here is to get the bandwidth, because this is, you remember, a resonant structure, the bandwidth and the loss together down. And then you've got to figure out how to make these in very long lengths, and that's a lot of good engineering. And then you've got to figure out how much are they going to cost, and are the benefits worth it. So the current state of the art, as far as I'm aware, but you never know what might happen at this conference, is given here, which we reported just this year, 11-kilometer structure, a 200 nanometer bandwidth, but it's still 5.2 dBs per kilometer, which is just not good enough for most applications. So you're not going to do an unrepeated transatlantic link with that, that's for sure. So what's the problem? The problem is a form of surface scattering which does not normally occur in conventional fibers, which doesn't have an air-glass interface. And that appears to be fundamental. There are ways that people are looking around it. If you use a lower temperature glass, you might be able to win on that one. But we're stalled out at a figure of a 1 or 2 dBs per kilometer at the moment, which is not good enough. So we just got to try harder, right? But we're already at the point where these fibers are of interest in data centers. Now, I happen to be fortunate and bump into an ex-ORC alumnus, Catherine from Facebook, and she told me this fact, that there are 20,000 kilometers of fiber per data center in Facebook alone. I didn't know that. That's just about the circumference of the world in one data center. And of course, the thing they really care about is the information flow per unit area and latency. And of course, the hollow core fiber, because it's not traveling in glass, the transit time is 30% lower. So that's my point about increase the speed of light in the fiber. But the transit time is better. And now, there's a new kid in town called the anti-resonant fiber. So called because this structure here shows that, see it's black? The glass is black. That means there's no light traveling in it. It's anti-resonant as opposed to resonant. And that means that there's very little power traveling in the glass structures again. So a number of people have started to work on this structure. It has some beautiful characteristics, especially for high power transmission, but that's another story. And you'll see that just that simple structure there can have a loss of about 1 dB per meter note, and this is not per kilometer, over a very broad bandwidth indeed. Now, there's something else you can do, which nobody to my knowledge has done yet, but who knows, is you can put a second ring in there. And if you put that second ring in, the loss on paper drops by another factor of 100. And that would give us an extremely low loss fiber. So we're waiting to see whether that is actually true and whether that can be made. And then you ask another interesting question. Is remember that glass really isn't important anymore, which is, so why are we using silica? Why don't we just go off and use really cheap glasses? And in some applications, I think this is going to happen, or possibly even polymers. So what's the thinking there? Well, if the silica costs, I worked this out, about $1 million per kilogram. That translates to about $10 a kilometer. And of course, this stuff, with 10 to the 6 dBs per kilometer, if you just dig it up, costs a few dollars a kilogram. So you can see that there's some potential there, and we've indeed started working. This is Francesco Poletti, who is here, if anybody wants to go and ask him about this. One of his early results, which shows a fabricated fiber just using Pyrex, right? Really cheap Pyrex. And you can see that this was an experiment done really for power delivery, but 1 dB per meter is possible using Pyrex, which has between 1,000 and 10,000 dBs per meter loss, just because the light isn't traveling in the light. So watch that space. That's really interesting. Now, for the rest of my talk, what I want to do is actually move away from fibers and talk about, I don't have any sound for some reason or other, but this is a movie which kind of shows what we're doing, which is that we are taking
and then converted to light just to be sent into another fiber. This can be compared to commuters having to get off one train and run to the connecting train in order to arrive at their final destination. It slows down the journey and uses a lot of energy. If the entire system used nothing but light, then everything would change. And that is one thing that nanophotonic metamaterial research is trying to do, create switches that work only with light.
Now that's a crazy vision. And that one has been around in these plenary talks from me and others for a long time. And so what I wanted to do with the latter half of this talk is to just talk about some new technologies that are around the corner that might help us to become more and more optical throughout the network, instead of the hybrid that we currently have Now, I am not suggesting that anybody is going to actually do optical computing and processing within the routers. But what we can do and think about is moving optics through the router under electronic control if we had a material, a system that would allow much easier conversion from photons to electrons and back again. And there's some really interesting stuff starting to come about at the moment. And so I'm going to talk about these: silicon photonics, 2D materials, graphene, molybdenum disulfide, metamaterials, some of which you've heard about, some of which you haven't. So this is silicon photonics. Now, this is pretty mature stuff. And this is actually the vision put out first by Intel, who had a few spare fabs and thought that they could use them for optics, which was great. And you see that there's talk of being able to fully integrate in this case, a transmitter and a receiver. But I wanted to talk about whether you could get this stuff actually out there into a router and help us to go more optical. So you see here lots and lots of devices. I'll show you some more. These are ones from our lab. You see up here, this is a Max Zender up here. This is gratings. So you have a lot of wonderful silicon technology available to you. This is an interesting one. This is an MMI splitter for different wavelengths. So these devices can be made quite cheaply and quite easily to give us that wonderful thing that we've been wanting all this time, which is integration. So here's some examples. Again, high-capacity transmitters. Low-cost packaging is key, and we're not there yet with this stuff. We can do multi-layer photonics, and we can do wafer-scale testing, provided that we have ways of tapping into the optics. And that's something that, again, we are only just beginning to realize that you need to do. It's standard in silicon microprocessors. You tap on and look at the signals throughout. And the great bugbear of this technology, optical sources on a chip. You know, silicon does not emit light. Bad news, well, not efficiently anyway. Bad news, what are we going to do about that? So with that, I wanted to introduce you to the concept of high-speed silicon photonics at 2 microns, because you can do it. Everybody's going, well, hang on a minute, silicon doesn't absorb at 2 microns. True, but with some clever stuff, in particular boron implanting, we've been able to make a high-speed silicon photodetector at 2 microns. So actually, it's ahead of the fiber. So it's working in avalanche mode, 20 gigabits per second, and this is just a very early example. So this is a technology which is a little more flexible than you might have thought. So with that, as an introduction of kind of where we are today with integration and planar stuff, I wanted to look at 2D materials, because this is just around the corner. So what's 2D materials? Well, everybody knows what graphene is. That's largely an electrical material. But if you go up to things like MOS2 and various other of these chalcogenide materials, they have a band gap. We like band gaps in photonics, right? Because they give us photosensitivity. And recently there's been a breakthrough in our labs and other labs which enables us to make 4-inch wafers of defect-free CVD molybdenum disulfide. 1 atom thick or a few atoms thick, because you want to make devices. So there's a quick view of what it actually looks like. So CVD, and here's some devices. A 3D photonic band gap structure, in this case backfilled with germanium, antimony, sulfur by CVD. And then we have another problem. See, all of these things are actually happier in 3D. In other words, they tend to be very lossy, very thin films. So you tend to use them normal. And of course, what we like to do is to use things in waveguides. So you've got the same old problem that how do you use these things? And you have to convert them into some way of using a low-loss waveguide and then interacting with these thin films horizontally rather than vertically. So here's the classic one. This one goes back 20 years to my knowledge, but here it is, in this case with graphene on the top, and sure enough, you have to pull the power up into the graphene, just like we always used to do with LCDs and all of these other things, and you can make yourself modulators. So here is a new kid on the block. We should be paying attention. So, what about all the stuff that you've heard on metamaterials and plasmonics? Now, once again, this tends to be a normal incidence planar technology. So we have to figure out that. And what I'm going to show you is a few interesting devices. This is still in amongst the physicists, right? There's not too many engineers working in this area yet. So the stuff I will show you is a very, very early from Nikolai Zhelodov in my center, who's provided me with this stuff, and it's really very interesting. So here's the grand challenge. Can we take these new concepts, metamaterials, plasmonics, very thin films, and can we turn them into something that makes sense? So what we're able to do is we're actually able to make new materials which don't exist in nature. Now, they're not really new materials. They're just full of little structures that are smaller than the wavelength of light. And so the light just thinks it's a normal material because the structures are so small. And therefore, it has optical properties which we can engineer on demand at any point in time and space, in principle. And so you've probably seen all this, often made with tiny little ring resonators, so as that we can, excuse me, so that we can have incident light on these at a resonant wavelength, and we can change that to whether or not these little rings resonate. So we can think about making holographic displays which are variable. We can do spatial mode multiplexing on an optical fiber in principle, because these are very efficient and effective at splitting out modes. And how are we going to do this? Well, there's really three areas that these people are working on. Phase change metamaterials. Phase change is really quite interesting if it's small enough, because then it can be very fast. So that's the crystalline to the glassy state. You can also use coherent control of metamaterials, which I won't be talking about, but, and you can have reconfigurable metamaterials, because these things are very, very tiny. They're a little bit like nanomems. So you're working at less than the wavelength of light, not bigger than the wavelength of light. And that's what makes the difference. So here's an example of what you can do. So this is showing here visually a way in which you can write into a phase change material, in this case with a blue light, and you can switch it, which changes its index. And so there's an example of a lens being written, and then you can read this out using another wavelength of light. So actually, this is not that different from your standard CD, which uses phase change, right? Or DVD. But it's much smaller, and that's the key. So the other thing you can do is you can start thinking about using, we've already mentioned, these new materials, graphene, nanotubes, fullerenes, and so on, diamond, and we can think about actually having these metamaterials which are variable, as you see. And this is kind of a new concept. So now you've got to figure out how you're going to make these things move. Because if you can make them move, then you've got a material whose properties can be changed under light or voltage. So here's a very early experiment which has actually been done. These are now much smaller than the wavelength of light, so they can be very, very fast indeed. And you see what's happening here is that they're being moved just by applying an electric field across them. And here's another example where you can make a focusing mirror, so you can do beam steering. But notice once again, the challenge is to turn these into waveguiding devices, because that's what we like. These are all, as I said, normal devices. So that seems to me to be the next big thing that we need to think about. So, more than just fibers. What I've tried to do in this plenary talk is to actually think more about the fibers and the associated technologies which will contribute to the next generation of optical telecommunications. So, maybe in another 13 years' time, I'll come back here and run you through these predictions and tell you how right I was or how more likely wrong I was. So, my point was there's several disruptive technologies that are out there. And having a view, particularly in the fiber development that occurs in the high power world, where we're talking about 10 kilowatts of power going through an optical fiber. As always, these new disruptive technologies are materials-based. So, materials beget devices, beget systems. And these are the things that are worth looking at. The 2D materials such as MOS2 look really, really promising at the moment. And these things have lased, by the way, optically pumped at the moment. Even at room temperature, you can actually make a laser already. That's really interesting. And there's been pretty slow progress with this all optical internet vision, right? So guys, we're not trying hard enough. That's my view. So thanks for listening.